Welcome to class. In the last video, we started looking at first-order linear differential equations, which have this form. What we saw is that when this q of x term is 0, we get this solution, but now we need to figure out what happens when q isn't 0. Let's get started. We would expect that the solution to this problem, whatever it is, isn't too far off from this one. We haven't dramatically changed the structure. It's still a first-order equation. It's still a linear equation. It's still an ordinary equation. So we have reason to suspect that somewhere in the solution to this problem, I might have a piece that looks like this parameter times e to the negative integral p of x dx. Right? It might look something like this, except that I have no reason to believe that my parameter here is a constant anymore. Remember, q of x is allowed to be a function of x, and that might make the solution look more complicated. So what we do to compensate is we expect y to have the form, well, not a constant, but maybe some function. We'll call it mu for now, times that e to the negative integral p of x dx. We do still expect this factor to show up because of the structure of the linear equation, but our parameter may vary now. And so that is why this solution method, by the way, is called variation of parameters. Okay, that's great. Where do we go from here, though? Well, let's assume it is a solution. Okay? Assuming that y actually is a solution here, then we know the left-hand side of the equation should equal the right-hand side of the equation, right? Well, let's figure out what the left-hand side of the equation is. In order to do that, I'm going to have to take the derivative of y, so let's start there. In fact, maybe I should work over here where I've got a little bit more room. And by magic, that guy's gone now. Okay, so y prime of x, well, that's just the derivative of this guy. We've got that function mu in here times e to the negative integral p of x dx. Here we're going to need to use our best derivative skills. First and foremost, I've got to take a product rule. So I take the derivative of mu with respect to x times e to the negative integral p of x dx plus the derivative of e to the negative integral p of x dx times mu. Let's clean this up a bit. Nothing I can do here just yet. But when I take this derivative, I hope we see that I get the same thing. By using the chain rule, I get e to the stuff times the derivative of that stuff. Running out of room there. Sorry if that went off the screen a little bit. Just got the derivative of this power. So now, when I take the derivative of this, fundamental theorem of calculus helps us out quite a bit. Plus mu times, well, I just get back negative p of x times e to the negative integral p of x dx. So I'm going to pause for a minute because this expression just got really complicated and we don't need all of these fancy pieces floating around. I noticed that I've got this e to the negative integral stuff floating around, so I'm just going to give that a nice name here. I'm going to call this yc for complementary. C for complementary. I'll explain that vocab here in a little bit. But now I can simplify this a little bit and I'll write d mu dx times yc plus, or excuse me, minus mu p of x yc. And there, we have found y prime. Now, that was all a rabbit hole to figuring out what dy dx would be if the solution looked like this. And by the way, I can even clean up my solution here now and just write it as mu yc. So what happens now? Plugging it into the equation, dy dx we just found is d mu dx yc minus mu p of x yc plus, there's dy dx plus p of xy, so I get p of x times y mu yc equals q of x. And what do you know? These guys cancel, and I'm just left with d mu dx yc equals q of x. Now I'm going to pause for a moment, and hopefully you can see the beauty of the expression that we just wrote down. It's separable. I can just separate and integrate. And what that tells me is that mu of x on the left-hand side must equal whatever the integral of this big ugly mess is. But if you recall, mu of x is the name I gave to this ugly guy over here. So really, this is the integral of q of x over e to the negative integral p of x dx. Really, I should use a different variable here, but I won't tell if you don't. dx. So now I'm going to clean up this whole thing and write it a little bit more succinctly. Y must have the form. Remember, we had mu of x, which is over here. That is the integral of e to the positive, if I flip it into the numerator, p of x dx times q of x dx. And it's this whole integral, that's mu of x times e to the negative p of x dx, which is what we call the yc. So in other words, y should look like this guy times this guy. So let me get this clutter out of the way for a minute so that we can kind of decompress and exhale and review what it is we just did. There, much cleaner. So let's recap really quick. We were trying to find a general solution to this equation, a one-size-fits-all. And we looked at two different cases. We looked at when q equals 0, and we got this nice compact solution. But it misses a lot of information because it'll rarely be the case in general that q is equal to 0. So while this is a good start, it was missing some information. We thought that when q is not equal to 0, it would still have that same form. Notice I've still got that e to the negative integral p of x dx term, or factor I should say, except that this time we variated our parameter. We allowed the coefficient to be a function of x. But this is more subtly missing information, which is this is not an initial value problem, so we do not expect a particular solution like this. We'd actually expect a full family of solutions. Or in other words, we should expect to see a parameter like this blue one has. For a little bit of language, by the way, we call this yc for the complementary solution. And we call this pink piece down here, when we variate the parameter, a particular solution. Because it's only one solution in particular. So, to cover all of our bases, the general solution is actually just the sum of the complementary and particular solution. It is yc plus yp. That way, we account for Q and have a family of solutions.